Welcome back, dear students. Under Algebra number theory, we are now in Unit 2, Finite Fields and Polynomials. Now in lecture number 7, so I'm going to introduce the concept of irreducible polynomials. Let's get on to the presentation. So you know what is a polynomial is? A polynomial is an expression which contains a single variable of different parts with mathematical operations such as addition, subtraction and multiplication. And you know what is not a polynomial, which should not contain negative parts and square roots. Now we have types of polynomials, which means reducible and irreducible polynomials. So when do I say a polynomial is reducible and when do I say a polynomial is irreducible? Very simple concept. A polynomial which cannot be factored into product of two polynomials with the lower degree is called irreducible polynomial. Okay, so suppose if you have a polynomial, some 4th degree or 5th degree or 10th degree or whatever it may be, that particular polynomial has to be split as a product of two different polynomials with a lower degree. It cannot have the same degree, right? Then it of a lower degree, if I can, then it is called as reducible polynomial. If I cannot, then it will be irreducible polynomials. Is that clear? So I've given you some examples to think. Just have a look at it. So irreducible polynomials are also called as prime polynomials. So the other name for irreducible polynomials are prime polynomials, which has prime number as its power. So 7, how can I split up? So I cannot write 7 as 7 into 1. So 1 power. So if I'm going to multiply, I'll end up with x power 8. So that is impossible. So reducible polynomials are extensively applied whenever you see something dividing. For example, when you walk on the pavement of the road, you have some chains divided, right? There, that comes also the applications of reducible polynomials. Okay. Now, first problem. Test whether the polynomial f of x is equal to 2x square plus 4 is irreducible over z, q, r and c. So now we know what is z. Z is a set of integers, q is a set of rational numbers, r is a set of real numbers and c is the complex numbers. So now what am I supposed to do? I have to test whether this polynomial is irreducible or not. Now let me take this f of x as 2x square plus 4. So I'm just going to equate it to 0. Only after finding my roots, then only I can say whether these roots belongs to which type of sets. So now I just take that 2x square plus 4 equated to 0. I'll be getting x square plus 2, taking 2 outside as a common constant polynomial, taking 2 out. So I'll be ending up with x square plus 2 is equal to 0. So if I'm going to take that, x square is equal to minus 2. So what are my roots now? X is equal to I plus or minus root 2. Clear? Because I have a negative number. If I'm going to take a square root of it, I'll be ending up with plus or minus I. So now I in the sense, now where does this roots belongs to? Which set? I can say clearly, since I is there, since imaginary part is there, the roots belongs to the complex set. Clear? So therefore, the roots do not belong to z, q and r. So what will I say? How will be my conclusion now? The roots does not belong to z, q and r. Therefore, it is irreducible over z, q and r. Whereas, the roots belong to the set C, complex numbers. Therefore, the roots belong to C. Therefore, the polynomial is reducible over C. See the contrasting thing? Irreducible. If the root does not belong to the set, then I can call it as an irreducible polynomial. If the roots of the polynomial belongs to that particular set given, then I can say it is reducible over to that particular set. Hope you understood. Now the second problem is f of x is equal to x square plus 1 in zx is irreducible over z. They are asking, right? Now what is over z? Z is a set of integers. Solution. Given f of x is equal to x square plus 1 in z of x, it is given. Now x square plus 1 is equal to 0, which implies x square is equal to minus 1 and further implies x is equal to plus or minus I. Therefore, the roots, what are the roots I got now? I and minus I. Does they belong to z? No, they do not belong to z. Therefore, f of x is equal to x square plus 1 is irreducible over z. This will be my conclusion. It is irreducible. Why? Because the roots do not belong to or does not belong to the particular set z. Now let's move on to the third problem. Is f of x is equal to x cube plus x plus 1 which belongs to z2 of x is irreducible. They are asking us to check. So now f of x is equal to x cube plus x plus 1 in z2 of x. What is z2? What are the elements in z2? We know that it is 0 and 1. Now what do? I have to check whether they are it is irreducible over z2. So this is another way of finding whether the polynomial is irreducible or reducible. So in fact I can take these two roots. You know, these are the two numbers which are present in the set. So for us, we can go and substitute that particular value in the particular polynomial. So let's take 0. So I'm going to substitute 0. What will be my answer? My answer is 1. So 1 is not equal to 0, obviously. So the remainder or the value is not becoming 0. Therefore 0 is not a root. This is how we conclude. So 0 is not a root. Therefore 0 is not a root. Then again you substitute 1. 1, if I substitute 1 plus 1 plus 1 is going to be 3. Again 3 is not allowed inside the set. So divide it over 2. Then your remainder is 1. So then again remainder is not equal to 0. Therefore 0 and 1 are not roots of f of x. Therefore if I conclude that if they are not the roots of the f of x, then what can I say actually? Therefore f of x is irreducible over z2. This is another type of problem where we found out we had written the sets, that is the number of the contents in the set, and we start substituting the elements of the set inside the particular polynomial, and we had seen whether we got a remainder as 0. Since we didn't get the remainder as 0, then I conclude that the two numbers are not the roots of f of x. Therefore f of x is irreducible. Suppose if any one of the two roots can be satisfied, then you can say it is reducible over z2. Thanks for watching. Let's continue in the next lecture.